Hi Spring fans, welcome to another installment of Spring Tips. In this installment, we're going to look at the Apache Geode project and its integration through the Spring Data Geode project. Now, Spring Data Geode supports Apache Geode, and you might have otherwise heard of Apache Geode as Gemfire, right? So Gemfire is actually a product that has existed for the better part of 2 decades. It's been around for a long time, and it predates obviously it predates Pivotal. It predates the Spring team's time at VMware, but it was acquired around the time of the acquisition of the of Spring Source by VMware, and it's one of those things that if you've got a use case that is served by this product, then you absolutely know about this technology. It's something that you will probably have looked into and more than likely used. Right? It's one of those best kept secrets. It's a thing that just people have used without having to be advertised to, right? We've had so much success with people finding it just sort of naturally, organically. They're looking to solve a certain problem, and that problem, that domain, is distributed data grid technology, right? They want something that's able to act as a giant RAM cloud, replicated or partitioned across a giant cluster of nodes that supports, for example, caching of data for fast, lightning, quick access, for continuous queries, for analytics, and for WAN replication. That is to say, I want to take data from one data center and then replicate the data if necessary to other data centers worldwide, right? To get a consistent view of the data. And this is particularly valuable, this horizontal scalability and this infinite sort of replicability across different nodes. This is particularly useful in the cloud native world. Recall that, of course, Netflix, when they made their journey to cloud native, circa 2009, they talked about their movement away from traditional storage technologies like SQL-based databases, to distributed technology like Cassandra, something that has no single point of failure. Geode is very much in that same fashion. Now, when I say Geode, I am referring to Gemfire. Gemfire is the product, but we have since open sourced all that. So bit for bit, all the interesting stuff that you want and that you're going to want to use is in Apache Geode. And so while we're going to see different APIs today that refer in some cases to com.gemfire, know that fundamentally, substantially, it is an open source technology called Apache Geode, and really they're interchangeable at this juncture, at this point, right? And this is it's been a long journey. We've had a long journey to see this product open source. But Pivotal, as part of its commitment to open source, we open sourced all of our data technologies a few years ago. So Green Plum and our work in Gemfire, all these things, these big data technologies became open source. So we're going to look at that technology today. Now, I'm just going to go ahead and say it. I'm really sorry that this hasn't been done before. I'm sorry that we haven't had a spring tip on this before. Gemfire and Geode are, to me, some of the most interesting technologies under the sun. They are amazingly powerful. These are technologies that, as I say, we don't really have to advertise, right? And I recall at VMware we had customers that would come to us and say, "Wow, we just paid, some obscene number that could only ever be justified by justified through some sort of golf game, right? They'd pay for some sort of terrible price for this golf game, and they'd end up with these extra licenses of coherence, right? It wasn't like they wanted it. It's just what they had, right? And they'd come to us and say, we really want to use Gemfire, right? That's the technology that actually does what coherence does, but it actually does it. It has those features, and it's been battle tested, right? Fortune 100 companies, large chunk of them are using Gemfire. It's one of those things that even after we open sourced it, we're able to satisfy customers because they're continually happy with this technology. So this is one of those things where it's just been really, really good, right? It's just been really good for a long time now, and we haven't had to do any kind of traditional marketing to support that. It's also one of those things where because it works so nicely with Spring, and it's been within the Spring ecosystem, and because we've had people working on it for so long, it benefits, right? It benefits from Spring's simplicity, and Spring too benefits from its power, its flexibility, and so the journey with Gemfire, the integration with Gemfire, has come a long way. My goodness, I remember when it was first integrated into the Spring family. Spring source engineer Costin Lau was working on it. Right, he was one of the. If you look at the oldest code in the Spring Data Redis project, you'll see his name in there as well. I mean, he's also in Spring Framework itself. Right, he's one of the legends of the original sort of motley crew that formed Spring Source. And so he, having those excellent technical chops, was working on the Gemfire integration. And let's just be brutally honest here. The possible integrations that we could do with Spring circa 2010 or 11, were not as elegant as what we can do today, because the product itself has become much more developer centric. It has historically been a data analyst's platform. It's been a technology geared for data sort of people, right? People working in an organization that care about data provenance, and they care about data analytics and warehousing and all these kinds of use cases. And so for it to now be able to bridge that gap, to sit comfortably in both worlds, to have tooling and to have integrations available to both sides of the proverbial house, that's a rare distinction, right? A lot of technologies focus and even then don't necessarily succeed on one side of the house. So I think this is a really interesting technology. Now, people use Geode, which is, as I say, a giant distributed RAM cloud. Basically, it's a data grid, we call it. They use it for a lot of different use cases. They use it for buffering. So I've used I've used other technologies like coherence before in production, right? And this serves a lot of the same use cases. This serves a lot of the same use cases. Suppose I have a whole bunch of data that I want to buffer. I want to write it to a backend data store, but that backend data store is slow. That is to say, it can't accept writes as fast as I can contribute them. I can use this data grid to buffer those writes, to absorb them, and then, as possible, write them to the data store that's behind the data grid. We call that write behind. That interaction, that message exchange protocol, that's called write behind. If you want to read data, suppose you wanted to read data from something that is slow, right? You read data from a backend data store, but it's slow, but you want to make sure that subsequent reads are fast, right? So this is called read through. You read through the cache. The cache can then be programmed to read from the original source thing. It'll look up the record. It'll resolve the resulting record, and it'll return the record, but it'll then cache that record so that subsequent reads for the same key in this data grid will result in the cached object. And you can do things like expiration of values. You can say, I want to read through, but if this has been idle and nobody's read it or whatever for X number of minutes or hours or seconds or whatever, then go ahead and expire it. That way, the next time I read it, I'll be forced to resolve the original object again, and I'll get a fresh read. So you can do all sorts of very interesting things. These are classic cache patterns, and they're certainly, I think, common. And then indeed, you'll see that Spring has a cache manager integration. And so while I'd love to talk about the cache manager integration, something we looked at when we looked at, for example, the Redis support in Spring Data Redis, while I'd love to look at that integration today, we're going to focus on some of the more interesting features of Geode proper. I don't want to linger on too much on these lower level pieces. You can absolutely get them to work. They're not a big deal. But we're going to focus on some of the new integrations made possible by Spring Data Gemfire or Spring Data Geode, depending on what you want to call it, and the Spring Boot Data Geode integration. So that is a bit of a confusing name. That is not a library that's in Spring Boot itself. It is instead a Spring Boot starter that is provided by the Spring Data Geode team. Right. So if I pronounced it wrong, if I named it incorrectly, at least I hope I correctly articulated what it is and where you might logically expect to find it. Now, in order to do this, we're going to build a client and a service. So we'll do that here, of course. And just for the moment, there's not really a lot we can do here besides generate a new project. We're going to call this the server, okay? And we're going to use Lombok. And we're going to use the latest and greatest 2.10 M4. I'm going to hit generate. And then I'll build a client and the same thing. I'm going to hit generate. And that's it. That's my two dependencies. I have my zip files here, and so we're going to start with the server. And the server is going to be, as I say, a thing that will store data. Now, in Geode parlance, there's several moving parts to a given cluster. A server is a thing that stores data. It's a node that stores data. In a server, you have what are called regions. Regions are logical partitions. I should avoid using the word partitions. They're logical chunks of the server. They correspond to maybe a database schema, for example, right? You might have a region called people, and inside that region you have keys and values, right? It's a map. Ultimately, it's a dictionary, if you will. So you put a key in there, and you can resolve values from those keys. What kind of keys? Anything, really. Any complex object in Java, anything you want, a string, an ID, a foo, a bar, whatever you want, right? Can be a key and or a value. And you can use that to resolve these references. Servers are not your first port of contact, not your first point of contact with respect to the client. So a client is a thing that will talk to the cluster, and it will resolve data, but it needs to be dispatched, basically. There needs to be something that'll tell it where to find that data. And so that lives, typically, in a locator. A locator is a component that acts as a dispatch, as a load balancer and a service registry, if you will. It tells you where to find nodes, tells the client where to find nodes, and it gives it metadata about the topology of the cluster itself. Once that's been resolved, and typically the client will connect to one of many locators, right? You will typically have at least 3 locators in the application. Once it's resolved to one of the locators, it'll then find a node and it'll connect to that node, and then subsequent incantations, subsequent invocations will work directly with the nodes, right? The node, once connected, will give it will connect the client to other nodes if it needs to. So why do we have 3 locators? Well, that's a good question, right? We have at least 3 locators. So think about this. A locator is it's the brain for all first connections for clients. So it's pretty important. You don't want to lose this thing in the application when you need it. And so suppose I wanted to deploy version 1.1 of my locator code, of my locator node, and so I have to take the locator down. Well, of course, I need a backup, right? Well, first of all, you want a backup. So in case one falls, you have the backup. But then suppose I wanted to deploy version 1.1 of the locator of one of the running instances. Well, then I have to take that down. Now I'm down to 1, right? I have 1 instance, and so in this case, that thing, the backup, now needs a backup. So it's always good to have 3 at a minimum. You can have more, but there is a useful limit. There's not a technological limit, but there is a useful limit because these things are pretty chatty, right? So you want to you'll have at least 3 locators and maybe a little bit more, but after that the crosstalk can become pretty noisy for the network. So we want to limit that as much as possible, wherever possible. Okay. Now we are going to build an application. It is going to be a locator. First of all, is also a cache server. So we're going to say that this is going to be a cache server, but in order for us to do that, of course, we do need to bring in the requisite dependencies, don't we? So we have a few dependencies that we need to bring in here. I'm just going to go ahead and do this manually. Right now, these checkboxes, these starters are not reflected in the Spring initializer, which is a bit of a pity, but they're milestones yet, so early days. Keep in mind, I did use the 1.0 M4 support here. So Spring Geode starter and org Spring framework Geode, and the version is going to be 1.0 M3, 1.0.0.m3, and the next thing I'm going to bring in is I've already got Lombok, don't I? So I want to bring in the Spring Shell dependency here. So Spring Shell, org Spring framework shell, and that is going to be pinned at 1.2.0.release for now. And I hope that in time this dependency will just be provided for me. It'll be implied or removed or whatever by the Geode starter. But for now, just for our purposes here now, we'll leave that there. All right, so there we go. There's our bare minimum locator code. We're going to say that this is a locator application. In order for it to be a locator application, we need certain things in play. As I said, first of all, it needs to be a cache server, right? So it's a locator is both a node, a server node, and this other thing called a locator. So we're going to tell it to basically talk to itself, right? Locator's location is equal to 10.0.334, and you're going to want to remember that. That's a common default, so just keep that in mind. And then finally, we want to create because there is a duality here. We are both a server and a locator. We're going to create a configuration class separate and apart from our locator class. Static, our locator server part, set class locator configuration, and it doesn't need to be that way. By the way, you can layer these, you can stack these on top of the Spring Boot application annotation if you like, right? So at enable manager and start will be equal to true. All right, so there we are. There's our very basic configuration. In order for this to work, we need some configuration. We need some basic properties that we're gonna have in play. And so these properties are not yet in the auto completion, so they are spring.data.gemfire.cache.name equals random.value, and spring.data.gemfire.cache.server.port equals 0, and 0 of course tells it to find the first unused port and use that. Okay, so there we go. There's our locator node. Let's try that. We need to have locators running before we can have a server, so this is fairly straightforward. Okay. Okay, what did I do wrong? Let's see. We've got an error of some sort. Yeah, well, it looks like what did I do? Is that one too many threes? That might be, yeah. Now what did I do? It is complaining about an unknown host. Oh, localhost. All right, seems that's up and running. That's good. That's as we expected it to be. Now, what I'm going to do is I'm going to build a server node, right? An actual server, a proper server that's independent, because again, I will have many more servers than I will have locators. So I'm going to build a new package here, server, and this one, as you might imagine, is a fair bit simpler because it is a subset of the thing we need for the locator, at least for now. So server application, voila, okay, and public static void main string args, and here I'm going to say spring application dot run server application dot class args. Okay, very good. Okay, so there's our server application, and in order for that to work, of course, it needs to be a valid Spring Boot application, like so. And let's just take advantage of this copying and pasting. And in order for that to work, I think that's it. I think that's all we need, actually. I think that's the... Let me just think about this for a second. Yeah, I mean, for now, that's probably right. Okay. Now, we have the server. And in the server, I want to define a region, right? And so the region I need to define somewhere. And I'm going to do that in terms of an entity. And that entity I'll store in a common package. And now, naturally, you could, and you more commonly would, extract this out into a separate common package and create an entity of type whatever. And we're going to store those entities here. I'm going to create a thing that stores temperature sensor data, right? This is a domain, very much inspired by demos I've seen by Spring Data Geode lead John Bloom and Geode subject matter expert Luke Shannon. So I'm going to go ahead and just borrow or appropriate that sample because I think it works quite well. So suppose you have high-speed sensor feedback indicating the temperature for various cities or regions in the world. Okay, so we're going to have a type here called a temperature that is going to store information about, guess what, temperature readings. So of course I'm going to use Lombok. I love Lombok. It makes my life just that much easier. And it's going to be an object that's going to be stored in a region, and that region I'll call temps, and I'll have a ID here like that, private double temperature, and private string city. All right, there we are, and ID. Okay, so there's our Spring Data mapped type, and I want to tell my server application about this thing that we've just created. So I want to actually include it in the scan of the code, right? So I'm going to include that plus the actual application itself here. So I say component scan base package classes, and I'll tell it to find server application dot class and temperature dot class. Okay. Voila. So there we are. We're just overriding Spring Boot's default component scan behavior so as to have it pick it up that component. So now we could restart the locator. I'm happy with that. Let's go ahead and now restart the server after we change our configuration. So server, very cool. Apply, go. All right, we've got a locator and a server up and running, so that's very good. Now, we're going to come back to this, right? We will certainly come back to this, but for now, let's go ahead and trudge, make progress on our client. And in the client code, we have a, let's see here, we have a zip file, cd client. Oh, we've got that UAO client.zip. All right, and in the client code, we're going to do the same thing. We have the common dependencies, so we'll copy, do some copy pasta there, copy and paste those dependencies from here, and paste those into pom.xml. All right, very good. So that saves us quite a bit of setup and ceremony, which I'm happy about because I loathe ceremony. And in the client, let's get rid of these packages just as before. We'll have a separate package here for client, and then therein we'll create a class called client application, and our class is a Spring Boot application, string arguments, spring application.run, client application.class args. Alrighty, very good. So there's that. And our client application is going to do a few things. It's going to actually connect to the data store. It's going to write data to the database for us. Now, in order for it to do that, it's going to also have that common type, right? So we're gonna have it talk to our region, and so we need that same type. This is where it would be useful to extract this out into a separate jar and then share that across. But for our purposes, just to keep things as simple as possible, we're gonna just copy and paste. Okay, this is not necessarily what you do in a typical application, but again, for our purposes. And there are two components here. There's the server that actually stores the data. So you're not gonna, that's gonna be a separate thing, right? That's gonna be independent of what we have here. And then in the client application here, we want to build an application that will take the data that it sees and turn that data into regions. So I'm going to say @enable entity define regions base package class will include temperature.class, and we're going to @enable cluster definitions, right? There we go. So, sorry, @enable cluster configuration. I knew that'd look weird. All right, so we've got this now. Now we've got our basic client application, and this is just this part's super familiar, right? This is I think for most of us our happy path, right? This is like the thing we're all used to doing. We take a type. I'm going to create a repository out of it. Extend the CRUD repository here. It's going to manage instances of entities of type temperature whose primary key is of type long. We'll save that, and then we're going to create a thing that writes data to the database like so. Implements application runner. It's going to be a thing that gets initialized when the application starts up. So application ready event. And there, we're going to be given a callback when the application starts up. So implement those methods. And we'll say @component. Application listener. Alrighty. And voila. Okay. There's our event. And what we're going to do is we're going to, when the application starts up, write data to the database. So we're going to use the repository that we've just created, that Spring Data is going to create for us. We're going to inject that repository here to do that, creation, reading, updating, and deleting in data. So we're going to do that here when the application starts up. So let's just create a very simple flow. I'm going to say, okay, find everything when the application starts up, and then for each one of those, I'm going to call this .temperature repository.delete, right, like so, passing in t, right? Okay, so, and that of course is a method reference just waiting to be used. There we go. So now we've reset everything. If we have any data, it's all gone now. And then finally, what we want to do is we want to write some data to the database. So we're going to insert some data. Insert, and then we're going to say for int I equals 0, I is less than int max, or I suppose it's int start. Let's do offset. Okay, we're going to start from a random offset. So what do we want? We want to say math dot, new random dot next int, and the int will be let's say 1,000 int random offset. Okay, I'm going to say random offset I++, so it'll be plus 100, so that way it's guaranteed to be at least 100. Okay, and once that's done, we're going to write data to the database. Okay, and here I'm just going to create a little method that'll actually handle the insert for me. Okay, and that insert will code now, and that insert is going to just be fairly straightforward, code. We're going to say, let's create a new temperature. I don't actually have a sensor to connect my application to, so we'll do it the old-fashioned way. Write some data manually. Okay, so new random dot next long, and the next value that we want is a the temperature. So new random dot next double, and then we need a random city, and of course I'll extract that out into a separate method, make it easier. And so string cities, San Francisco. I'm in beautiful Toronto at the moment as I write this. San Ramon, San Gabriel, Los Angeles, Paris, Shanghai, Tokyo, Seoul, Cairo, etc. Okay, so I've got now a bunch of cities. Let's go ahead and create an array, divide that there, and now for each city, for string city in cities, I'm going to write the data to the database. For each city I want to return a random one, don't I? So I've got a hardcode list. I'm going to say return new random dot next int cities dot length int index. Okay, there's my index. I'm going to say returning cities index. There we go. Okay, so I'm just going to generate a random one that's bounded by the number of elements in the array, and I'll return a random offset into that array that's bounded by that, so it's not going to be any more than that. Then I'll use that to create this temperature object. And you'll notice that I've got a number of different cities that start with San, right? So we'll use that later on to demonstrate some analytics capabilities. Okay, so now we've got that. We've got the raw one. Now let's save it. So this dot temperature repository dot save, passing in temp. All right, so there's the saved record. Fairly straightforward if you've ever used Spring Data. And now I want to say this dot temperature repository dot find by ID saved dot get ID. You know, I want to say if it exists by ID, and then I want to map it. I want to say give me the ID, of course. So temperature get ID, and then or else. No. Okay, so there's that ID. And what I want to confirm is that the ID that I've returned from my cache matches, right? Is true. Let's try that. This is a Spring Framework class, good for production code, good for DBC, design by contract kind of assertions. I'm going to say is true equals is equal to saved dot get ID. So I should be able to write the data in and then pull it right back out. Okay. So let's see. Should exist in the database. All right. There we go. So there's my updated code. Very cool. Okay, so now we've now written any number of records here, right? Randomly when the application starts up, we're writing data to the database. Now, I think that's actually a pretty good first start. Let's go ahead and just see that that works. Now, before we do that, let's connect using Gfish. So I'm here in this console. I'm here in the Apache Geode distribution directory. And I'm in the bin directory, and I've got a number of shell utilities, including something called Gfish. This is a Gemfire, or I suppose Geode shell, right? Within Gfish, you've got a lot of capabilities here. So I can say, okay, I'm going to connect, and it'll ask me to connect given a locator. Well, you saw how that works before. So I'm going to say just connect, and by default, it'll connect to localhost 10.0.334, which we already did before. I could have said connect -- locator localhost 10.334. By the way, this shell, does it look familiar? You might recall from our Spring shell Spring tip video from a little while back that these capabilities, these are things that you would get in Spring Shell. That's because Gfish, the shell, is based on Spring Shell. It's based on the same project. And in fact, you might even argue that it was birthed because of its need to integrate and support Gemfire. Okay, so now what? We want to say list regions. Let's see if we can do that. Nothing found yet. We haven't started the client either. Let's do that. So let's now run this. We know that we have this thing. Gonna find the region there. Good. Hit run. Uh-oh. What did I do wrong, huh? No available servers with which to connect. That's because I need the configuration in the property file for the client. Okay, so you can't, same thing. There's a bit of configuration implied here when using the client, just as we had for the server, but the configuration here also is not yet supported through the property auto completion in in Spring Boot, but that's on the way, right? So for our purposes, it's not a big deal. It's just one simple client. We say spring data.gemfire.pool.locators equals localhost 10334. Look familiar? Okay, take 2. All right, that seems to have run. It didn't stay up because there's nothing to stay up for. There's no, it's stateless, right? It just starts up and does what it does, and then it shuts down. There's no like web server or server socket or anything. It is not, in point of fact, a server. And so we can go here now, this region. So you can see that it now knows about our temperatures, right? So it is clearly able to work with our temperatures, which is kind of cool. We actually also have data in there, and we can run a query. So let's do a query. Query equals, and then it takes something called OQL. OQL is the object query language. So I can say select count from temps, right? Actually, let's just do that. There you go, 374. Let's look at particular records. So let's say I want to unpack the ID and the city. Okay, there we go. Or the ID, the temperature, and the city. Now, because it's actually, first of all, keep in mind, these are the records in the Java database, right? In the Java code. I didn't teach Gemfire or Geode anything about our data. I didn't tell it how to persist this. I didn't even implement serializable. All I did was annotate it with that region, and it just kind of implied the layout of this object using reflection, right? This is not the only way you can store data, right? You can actually use you can see that it's working, right? First of all, it's working just fine with this format. But this isn't always the best situation. Suppose I wanted to run queries against some of the fields in a much more sizable data set. In that case, I would need to the engine, the database platform itself, the analytics platform, needs to unserialize or deserialize rather every single temperature Java object in the cache, then run a test against it, and then it would, if I wanted to run a condition or a test against just the predicate, for example, I'd have to deserialize that, or I wouldn't, but the platform would. It would deserialize the object, dereference the temperature value, run whatever query or predicate we want against that temperature value, and then continue on, right, accumulating the results into a result set. That process slows things down, not a huge amount, but it does. And if you want to avoid that, you can. There's a thing called PDX. This is an encoding format that is proprietary to Geode. Other data grids have a similar thing, right? So, for example, if you're using coherence, they have something called POF, portable object format. So it's the same idea. It's a interface. It's a type definition language that you define that is agnostic of any one particular language or runtime, and it is basically you basically define the layout of the object, right? It's a type def basically. If you've ever done C, you're telling it, or a struct rather, you're telling the runtime how memory is laid out and what fields go where, and if I look at the third field into the type, what can I find? Is it a string? Is it a date? Is it an object? Is it a Boolean? Etc. And so that discussion, that understanding, helps the runtime because it can unpack just the one field that you're looking for, right? It's not just going to unpack this blob that is your Java object, and then call that method based on reflection. It can say, oh, you're looking for the temperature, the field called temperature that I happen to know is a double, and so thus it's this many bytes offset into the payload. And you can see actually behind the scenes, it's cached the PDX type, right? It actually has that definition. It's creating it for us automatically. But if we give the runtime that PDX up front and we store things explicitly up front using PDX, then we get some performance benefits. You can implement in your types here, implement PDX, what is it, writer? Yeah, writer. And then if you implement that, you've got these methods you've got to care about. So I wouldn't use that. You've also got a separate type that you would implement generic, independent of any particular entity, called PDX serializer or encoder, something like that. It's a thing that you pass entities into, and it'll know how to encode those. So these are things that do this work for you. Normally you wouldn't implement all the methods. You could extend from a base one, so extends PDX, not writer imp maybe, right? That's that. What does that give me? Yeah, so you have to, something like that, one of those types, right? There's a base one, and as you can see, I haven't done it recently, but that works if you need high performance. And the benefit of that is that you're forced to, in unpacking your type and explaining it and articulating its structure, the shape of that type to the runtime, you're forced to make concessions to the fact that this is just a bunch of bytes at somewhere, and that those bytes have to be readable. But when you do that, you make it possible to now then take that PDX definition, that type definition that you've explicitly defined as opposed to we've implicitly defined here, and use that in other platforms. So you can read that same type from .NET, from C, from C++, whatever, right? And there's bindings. There's lots of different client libraries that let you talk to this grid. So this can be a great integration store if you want to have a place where services can integrate with each other. They can, you can have C code reading the data off the sensor hardware, right? And that could be writing to this grid, and then Java code could be doing complex event processing with that data. Okay. So let's talk about processing. Let's talk about analytics. First of all, I would like to actually process some of this data. I would like to be able to run a query against that, and you can do that. You can create a custom finder method in the repository. It is just Spring data after all. But what I would like to do is I would like to create a custom finder method that notified me when data is available, right? And this is a different approach than perhaps you are accustomed, right? What I want to do here is I want the thing that I want the data grid to tell me when there's new data, as opposed to me constantly polling the data grid, going through all the results on the client, and then finding the record that matches my condition that perhaps didn't match that condition a second ago or a minute ago or a week ago. Again, I've only got a few hundred records here, but it is not uncommon to have billions of records. So this is large scale, big data in the truest sense. So it would be inefficient and regrettable if all you did was use Gemfire as you might a SQL database to pull down data and process it. Or if you're going to treat it like a SQL database, at least treat it like a SQL database and use some of the more interesting features of a SQL database, right? The equivalent of a stored procedure. So what I want to do here, and it's not even like a stored procedure really, it's more like a complex event processing engine that happens to run like a stored procedure, right? What I want to say is, when there is a fact that is true, let me know. I want the grid to be responsible for running a query, and when there's a result that matches, let me know. But I don't want to be bothered with constantly pulling the grid and having to pull data down. That's really inefficient. The grid can run the query for me. It can distribute the query across the grid instead of me distributing the data across the grid, right? And so we're going to do that. We're going to create a continuous query. Okay. Now, in order for us to have a continuous query, we need to write a little bit of code here. Not a big deal. We're going to create a new package in the client module. CQ Java class CQ application public static void main string args spring application dot run CQ application dot class args, and voila. Okay, so that's the skeleton of our class. It's a Spring Boot application, naturally. We want to say enable cluster configuration. Great. And then really we could put this continuous query anywhere, but what's going to happen is we're going to start this application up. We need to make sure it doesn't disappear. So I'm going to say new scanner system dot in dot read, isn't it? Next isn't it? Yeah, there you go. Next, so it's going to parse for the next token. And we're just going to have a continuous query here. So let's at continuous query. And the name of the query will be new temperature readings. Kind of immaterial, but nice to be precise. Select all from temps where city dot contains SAN. So see what I'm doing there? I'm actually writing a query that uses the objects, right? It is a Java object. I can say dot contains. Here I can do the same thing. I can say dot substring, for example, 03, right? And I get back just the first 3 records. I'm actually calling the Java methods on string. So I'm going to say when that method gets called, when that query matches on new temperature, give me the CQ event, and then I want to process that. I'm going to say, okay, if the event is there, I want to unpack it. So I'll say, this dot get new value, and you can see I've got the old value, I've got the key, I've got the query that affected it, any exception, I've got the delta, the difference, in bytes between the old value and the new value if I want, lots of interesting information. But what I want is the new value, and I'm going to say if present, I want to map it to a temperature, right? So I'm going to say temp, and I'll just print it out. Okay, so system out temp dot to string. And of course, this could be CQ event. Very good. All right, so there's my CQ method. So basically, whenever there's a fact that matches this query, whenever there's a record that's been written into the database that matches this query, this method will get called, and I'll get a chance to process it. Right? I can write it out. I can do interesting things with that. So now I've got the CQ application. I've got the client. Let's go ahead and run this. Okay, we'll run this code, and we'll see that should hopefully stay awake. And nothing will happen when it starts. It'll just sit there and sort of wait for input or wait for something to write down to the output. One hopes. Okay, good. So there's that. Now, let's go to our client and run the application again. And I'm going to quickly switch back to the CQ application once this is up and running. So we're in the CQ application. It says started CQ application. There we go. You can see that almost immediately, all those writes that I've just done in the other thread, in the client application, in the other process, that match SAN, and there's a few of them in our data set, are returned immediately, right? Instantly. It takes no time at all. And that would be true were we running on 1,000 nodes or just one node, as I am in this instance, right? So that's pretty cool, huh? I like that. I mean, I love continuous query. You can use it for pub sub kind of things. You can say, okay, I'm interested in any new messages. Well, what does that mean? Well, give me a continuous query that selects all from messages. It doesn't get simpler than that, right? Notify me when there's a new message. What about a new message in the chat? Okay, just select all from chats where session ID equals whatever. You can do all sorts of very interesting things here. Okay, I like that. But what if I wanted to do something that I couldn't really articulate with OQL, right? OQL is the object query language. I like the object query language. But a lot of times I need to do custom processing on the data. And here too, Geode comes into its own, because if you want to do something with Java code in a SQL data store or MongoDB or anything like this, you have to pull the data into memory. You have to pull it into the client and then stream through the data in the client. And you can't, unless you go out of your way to bring in threads and so on, you can't really parallelize any of that work. And certainly if any of that work is IO bound, you're not going to be able to scale that up, infinitely. Certainly you're not going to be able to scale it up on a single node, a single instance. So now you have to get into the business of trying to parallelize it across different nodes. And sure, there are technologies like Spring Batch, remote chunking that support this. But again, now you're in a whole different paradigm. What I would like to do is to say, here's some functionality for processing I would like to do. Please run the processing logic across all the regions in my system. Okay, and this is what we can do with custom functions. Okay, and these functions, they can do some very interesting things. They can do some very interesting things that you might not have thought about. Like, for example, one example is, let's suppose you've got a bunch of CSV files. This is a common example that some people have, and for data ingest, they want to load a whole bunch of records into the memory and then process it, and analyze it and so on. But they need to load the data. The ingest itself is tedious. Well, suppose I had a cluster with each node in the cloud platform. And by the way, cloud technologies are great for this because this thing can scale out horizontally and infinitely and dynamically, right? So if you're using something like PCC, the Pivotal Cloud Cache on Cloud Foundry, then that's just a no-brainer. You just deploy it and you can talk to it from any of a number of different nodes. If you're on an IaaS platform, something like AWS or GCP or Azure, of course, also great choices. I mean, and let's suppose you had such a deployment, such a topology. Each node, each virtual machine on the IaaS might, for example, be connected to shared storage, right? You have you have a mount where you can read data. You've got batch data, CSV data, whatever. Each region, you can actually write to the grid a whole bunch of keys, right? The keys could be just keys and then empty values, and then you could run the processing, and that'll be fairly distributed across all the nodes in the cluster, right? So it won't just be on one node; it'll be load balanced. And if you want, by the way, you can specify redundancy. You can say, for this node, please replicate it to this other node, right? For example, or you specify that you want to replicate it a number of different times. You can even get transactions, right? You can actually ask the data store to say, I insist on being able to roll this back if something goes wrong. There's even support for JTA in Geode. I mean, it's got everything. It really is just a enterprisey, well thought out thing, I wouldn't use JTA, but if you need to, the point is this is one of those things you could use it with. You could use it with that and, for example, JMS or whatever, right? And it also has logical resource local transactions. That's the other thing. You can do multiple writes and then transactionally write them or roll them back. I mean, these are all sort of beyond the scope of what we're going to talk about here today. But you can also insist that when I write, I insist on having a guarantee that it's been replicated across 1 or 2 or 3 or 5 or n or some other strategy that you arrive at, whatever strategy you arrive at for determining how many other nodes. You can insist on achieving that minimum sort of replication set. Okay. So yeah, like that is one of the really, really compelling features of Geode. Now, I want to run a function, and if I had this data ingest scenario, I could, for example, insert a bunch of keys into the cluster, and then I could run this function that visited each node in the cluster, and then I could look up I could find all the keys that use the current node on which the function is executing as the lead node, as the master node, as the node on which this write was first written, right? There's other nodes, there's secondary nodes that have the write as well, there's a replication nodes, but this is the leader node, right? I can write to all of these different leader nodes, and I can run the function. I can say, if I am the leader node for a given write, I want to process the keys that were in that write, and I would then read in my function on that node all the CSV files that match the keys that are resident on that node, and no more. And that way I would be charged with, I would read whatever CSV files I need to read on one node, and all the other nodes would read the CSV files that are resident to that node, and that way it'd be parallelized. And I could just invoke this function once from the client, and the work gets farmed out across, n nodes in the cluster. It could be 2, it could be 1,000, right? You can parallelize just any kind of work like this. So you get nice logical distribution, even if you're not concerned with just data sharding. If you just want a fair scheduler, this is a really interesting thing to have. So let's write a simple function, nothing quite so complicated as what I've just articulated, but interesting in of itself. Okay, so what we're going to do is we're going to write a function. We have to create a client-side view of that function. Okay, so we're going to say average temperature function. Okay, invoker. I don't know, you can call it whatever you want, and it's just an interface, right? Very, very Spring Data-ish, right? And I'm going to say I want to run this function on the region called temps. Region called temps. All right, and it would be nice if you spelled this correctly. I clearly am not capable of that. but you don't actually have to, right? There's no importance. No importance is placed on the name of the interface itself. That is not true, however, for the name of the function. I think we can just do this. I think we can say double average temperature. Okay, let's try that. So that's the name of the function, and we have to define that function in the client. So actually, before we, or rather in the server, but before we do that, let's inject that code and get that working. So private final average temperature invoker, call it invoker, add the arguments, and here invoke function. So I'm going to say dot average temperature, and that should visit each region and calculate the average of all the temperatures in that region and nowhere else. And then from there, I am going to visit each temperature there and calculate the average. So average to double, and I'll just say x equals x. It's an identity function, and average cluster average. All right, and we just write that out. So I'm going to use Lombok here because I'm nothing if not lazy. So I'll say log.info cluster average, and voila. All right, there's my cluster average temperature. Okay, so we now need to write the processing code, and as you can imagine, our function is going to look pretty similar to this. Okay, we didn't. I hate to spoil the plot. I might have extracted this out into a common method that is shared between client and server, but you know, that's cool. I'm okay. I'm happy leaving it like that. So let's now go back to our server. All right, and in the server code, in the first things first, we need to tell the locator about the function. So we're going to do that by creating the function, and the function will be in a place that is in the server. Okay, and we're just going to implement the function. It's going to be called average temperature function imp, for example. It doesn't have to be called, I mean, it can be called whatever you want, really. And it's just a string bean at component, and it's going to be a Gemfire function, public void calculate average, or no, it's average temperature, isn't it? It's this method here. And I'm going to inject the region data. It's going to be a map of string to temperature. Okay, there's the data. And I need to tell my locator about that. So I'll say that this is it's going to have to do a component scan, looking in there. Okay, and redundantly, I'm being redundant here, but just in case, pretty sure you don't need that. Okay, so there's my component scan there. And do we need the same thing in the server? We might need the same thing in the server. I'm not 100% sure, but I think we're okay for now. Let's go ahead and just leave it out for now. Yeah, that should be okay. That should be fine. So let's try that. That's the function. That's the locator. Okay, so we've got that. Going to go ahead and restart the locator itself. And actually, you know, before I do that, I should implement this. So I'll say data.values.stream.map temperature, get temperature, and I'll say I want to get the doubles, so averages for all the data in this current region, right? In the current node I'm processing on. So I'm gonna get all the data from there. I'm gonna collect it. So actually, I don't want that. I want to say .map.collect average to double XX, identity, right? Same as before. Average. Okay, and we'll use lumbuck here, so log for j, and I'm going to say log.info arrived at average average. Okay, and then we're just going to return the result. Return average. I think I need the return type. That makes sense, I suppose. Let me see. Do I want a return type? I suppose I do. I want the double. And that double is going to be the average. Alrighty. Okay, that looks good. I think we can leave it there. Now, yeah, that's fairly straightforward. Let's just leave that there. And we've got the little log statement to confirm that we visited this node so we can actually see the work fan out as we want to. So we'll restart this. That's the locator. I'll restart that first. We need a locator. Oh, I did it again, didn't I? Rename average. Okay, that's fine. And then the server, restart that. Okay, let's go back to Gfish just to confirm everything is as we expect. So I'll do connect by default. Good. List functions. There's our average temperature function. Oh, it's in there twice. Average temperature function delete or remove. No, region temps. No, that's not what we want to do. I mean, there we go. We've got that. I mean, should be fine. I don't know. We'll be okay. Okay, let's see what happens. So that's this. You know, we could actually make it a little bit simpler. So let's just, so that we know we're on the same page. This will be the it'll be called average. We're just gonna call it average, okay? Very, very boring, but that way we know what's happening. So let me rewrite that, and we'll restart the client. Restart. All right, so we've got the average. That's the client application. Return this, or run this. All right. Whoops. Right, the function is not registered. Fair enough. So let's go back over here and restart the locator. Good. Server. Okay, and now if we go to list, we go to connect list functions. There's our function average. Oh, it's in there twice. Okay, so that actually does, that has the effect. Okay, so there's that, and then we go back to our client application, and hopefully this will work. I'm not sure if I have to return object from the function invoker or if it can be downcast like this, but we'll see. Worst case. All right, that seems okay. Did we get the results back? Did we even bother? Client application, cluster average. Look at that, 0.49. So that invoked the reads across. It did the calculation across the cluster. We can confirm that by arrived at average blah 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 on this one server node. So again, if we had more than one node, we'd see that printed out at every single instance. All right, my friends, we've only begun to scratch the surface. I hope you can appreciate some of the opportunities here. We didn't even look at the cache manager. We didn't even look at the basic key value store. I feel like treating Gemfire or Geode as just a regular key value store is a bit misguided. You're really missing out on some of the most one of the most high-speed, one of the most scalable systems in the world. So hopefully you've gotten something out of this journey. Thank you so much for watching, and as always, we'll see you next time.